Okay. Okay, so let's get started. Welcome everyone to the One More Machine Learning seminar today. So today we're very happy to have Ting Lin to speak to us. So Ting is actually a third-year graduate student in Peking University, and I believe his main area of research is on analysis of finite element methods. But in his spare time, he does very good research in machine learning, in particular some approximation theory questions in deep learning. And today he's going to talk about universal approximation properties of deep neural networks from a control theory perspective. So Ting, please.
Okay, thanks, Qianxiao, for the warm introduction. Okay, today I'm talking about the universal approximation properties of deep neural networks using a control theory perspective. This is a joint work with Chen Jingpu, Li Qianxiao, and Shen Zuowei from National University of Singapore. So neural network has gained huge success in various areas, and the key insight of neural networks is that for mathematicians is that it can learn very complicated functions. Okay, for example, we can consider a very simple binary classification problem. In this situation, machine learning is just to learning a function as an indicator function from RD to 0, 1. Okay, so the task might be very easy since we only want to learn an indicator function with probably two values, 0 and 1. But it is still very challenging because the level set can be very difficult to figure out. So how to learn a function? Basically, there are two things, the model and the data. So here to learn a function, technically, we could decompose the whole procedure into three parts: the approximation, generalization, and optimization. And the other is correspondingly split into three parts. The approximation error measures the distance between the target function and the best solution based on our given patronized models, also called hypothesis space. And the generalization error measures the distance between the best solution and the best empirical solution based on our given data. And finally, the optimization error measures the numerical error based on our specific numerical algorithms and the specific given training data. So clearly, the last two terms, the generalization error and the optimization error, are all around the data. So this might be a bit more challenging because we actually don't have an actual data in our mind. On the other hand, the approximation error only quantifies the expressive power about the hypothesis space. So the first, and to be honest speaking, the most straightforward thing is analyze the approximation problem, since we can regard the whole machine learning problem as a pure analysis problem. So here we should provide a precise definition. We say a function class f has a universal approximation property. If for any continuous function f, we can use the functions in curly f, say phi, to approximate the function f with arbitrary small error. So here the norm is usually taken as LP or L infinity if we want to focus on the approximation problem, or we can use some empirical norm if we want to focus on interpolation problem. So the most famous example of the universal approximation property, or say universal approximator, might be the polynomials. By the celebrated Weierstrass theorem, we know that the polynomials can approximate any continuous functions locally in L infinity norms. So this means that the polynomials the polynomial space have the universal approximation property. It turns out that the polynomials are very, very essential part in the linear approximation theory, since almost all of the linear approximation algorithms finally will reduce to a polynomial approximation result. But unfortunately, this do not make sense for the neural networks, since the neural networks are highly nonlinear. So it turns out that we must develop some new tools to analyze the approximation of neural networks. Okay, so there are lots of results about the approximation of the neural networks, and also there are many types of neural networks. Okay, here we pick the ResNet to be our focus. Okay, the ResNet is proposed by Kami He and his collaborators in 2016, and after other seven might be 8 years, it has gained 180,000 citations. And just in last year, the 3 authors of the ResNet just awarded the Future Science Prize. Okay, so but despite its huge success, this popular and widely used structure is actually quite simple. It's just based on these so-called residual blocks. That is, we give an input x and we just output x plus fx. And the whole procedure is nothing but just stacking all the x plus f together to get a whole formulation like this. As I comment here, it is quite simple but still mysterious because to say it is simple because we're just stacking a lot of layers together, but to say it's mysterious because it has some unbelievable power in many practical tasks. So in this talk, we will study the expressive power of the ResNet. So here's the outline of these talks. So in this talk, under a certain condition, we will provide a general, a universal approximation property of general non-constraint systems. This is optimal for the ResNet. And the second, we will provide some universal approximation property for control systems that are subject to some symmetry. For example, we can consider the universal approximation property of CNN when regarding CNN as a shift invariance architecture. We also study the universal approximation property of the permutation-invariant architectures. The take-home message is that the composition and the stacking layers can achieve expressive power, albeit each layer is quite simple. Okay, so the way we study the ResNet is so-called the continuous time idealization. This means this is proposed as an idealization of this QuickTime ResNet, which is proposed by Professor Weinan E. So we just follow the 3-step approximation. First, we regard the ResNet as to the original composition form to the finite difference recursion form, which means that xk plus 1 equals to xk plus f xk theta k. Here, the xk is a state and the theta k is a parameter. So the ResNet is nothing but the output map from x naught to the x big N. The next step is that we regard the ResNet, the finite difference scheme, as an Euler discretization of the control system. And we just formally set the time step to 0. Therefore, the finite difference scheme might be converged to some differential equations, say d over dt xt equals to f xt theta t. Okay, here we formally said that theta k might be convergent to some continuous time theta, and xk converged to some continuous time xt. And finally, we formally said that f over dt might converge to some small f. Okay, therefore, the ultimate map of the ResNet x naught maps to xn can be regarded as a discrete approximation of x from time 0 to x from time t. Okay, this is just the flow map of the control systems or the dynamics. Okay, here I will use the term control systems or the dynamics interchangeably. And when we say the control systems, we actually emphasize the role that theta play with. Okay, now we can say that the dynamical system and control system is the continuous time ResNet. This idealization can be used in say, architecture design and optimization algorithms, and it turns out to be very popular. But here I want to emphasize is that the above 3 argument or the idealization is kind of not so rigorous. Since here, we use a lot of hand-waving argument to make all things converge to some continuous time path. But fortunately, we can make it rigorous in the universal approximation setting. This is verified by this theorem. It says that under mod condition theta, if the flow map satisfies the so-called scaling invariant, which means that if we have f in curly f, then we can imply that the constant multiplication of f is in the curly f. Under this setting, we can say that under mod condition on theta t, if the flow map with control family f has universal approximation property, then the output of ResNet has universal approximation property. The schedule proof is quite simple. Okay, first, we just use piecewise constant control system to approximate the general control system. This is a standard technique in, say, mathematical control theory. And the second step is that we use the standard Euler discretization to approximate the piecewise constant control system. Well, this is also classical in the numerical analysis. Okay, so here the two-step construction, we can transfer the original discrete setting about the approximation power or the expressive power of the ResNet into a pure control system. In a pure control theoretical problem, that is, what is the expressive power of A sub f? Here, the A sub f is the flow map of a given control system's f. Okay, here we can just consider the A sub f be a set of all piecewise constant flow map, because we have the first idealization. Okay, so here is the main result. For dimension greater than 1 and any function from RD to RD, if the control system family satisfies the following two conditions, first is that the curly f has a nonlinear function. The second step is that the second is f is affine invariant, which means that h in curly f implies any affine transformation of h is in the curly f. Then we can deduce that AF has the universal approximation property. That is to say, for any given p from 1 to infinity, any compact set k and any tolerance epsilon, there exists a phi hat in our flow map A sub f, such that the approximation, the error of phi, the error between phi and hat phi are less than epsilon. So we make two remarks here. The first is that under the affine invariance, the result is optimal. Because if f only contains about the linear functions, say wx plus b, then the flow map of x maps to x wx plus b is the linear map like this. So we can do the easy calculation to show that the linear control system can only approximate linear functions. That is to say, the system is optimal when we consider the affine invariance of f. The second one is that if we can reduce, we can weaken the affine invariance, say we under some restrictive affine invariance, which means that here we might not suggest all matrix and all vectors are in F. Then the result can be also established for many common division functions. And I'm not going to show the details here. This is the result for the dimension greater than 1. So how about the dimension in 1? So these are some observations from the continuous time ResNet, and this only makes sense for the continuous time ResNet. In the discrete time, we do not have such observations. Okay, so how for the continuous time ResNet? First is that in one dimension, the flow maps are increasing. Means that this follows from the fact that trajectories do not intersect for a simple ODE system. And I just showed the illustration here. Okay, in any dimension, the trajectory do not intersect. But in one dimension, we can make all things in some order. It turns out that the flow map must be increasing. The second observation is that in one dimension, the only increasing function can be approximated well by increasing functions, which means that if you want to use a non-increasing function, say the functions in red, to approximate the functions which must be non-increasing, like this, then the error must be at least this one plus this one, which is greater than the gap of the two horizontal lines. So combining both observations, we know that only increasing functions can be approximated well by the flow maps. Okay, now it's natural to ask whether it is the only constraint. Unfortunately, we can say that this is the only constraint of our undersetting. So we actually prove the things that the flow map can approximate increasing functions. Here is the rigorous statement for our one-dimensional result. Here for phi from R to R, which is increasing and also continuous, if the control family satisfies the two conditions, first is that f contains a nonlinear, non-quadratic function, and the second is f is alpha invariant. Then for any p from 1 to infinity, okay, here the p can take the infinity. Any compact set k and any tolerance epsilon. There exists a phi hat in A sub f such that we can make the error arbitrarily small. Okay, again, we say that under alpha invariance, the result is optimal. Okay, here we only need to verify the case that f contains a quadratic function. To say this, we consider the flow map of x dot equals to x squared and do some simple direct calculation. We know that we solve the flow map of the ODE systems to get 1 over xt equals to 1 over x0 minus 1 over t. And finally, we can solve the flow map, which is the x naught maps to tx naught over x naught minus t, sorry. So here, the map, okay, I should highlight that the map is always not so well defined in the global line. But if we fix some small t, then this term can be defined locally. Okay, so it can be shown that for general case, the flow map of x dot equals to a quadratic function of x has the form ax plus b over cx plus d, which is closed and forms the set of fractional linear transformation. So it turns out that if f contains only the quadratic function, then the flow map can only approximate the fractional linear transformation in one dimension. So it turns out that the result in one dimension is optimal. Okay, so in the previous, we proved the result in dimension greater than 1 and proved the result in one dimension. But here we both require that phi should map RD to RD. So, but in real situation, definitely there are a lot of cases that the output dimension does not equal to input dimension. So to remedy this, we introduce the concept of terminal layer. That is, for example, when we design architecture, we consider a stacking of residual blocks, which means that RD in, RD out, RD in, RD out, RD in, RD out. And finally, we add a terminal layer, which maps RD to R to reduce the output map in one dimension. Mathematically speaking, for a given function class, curly f, which consists of function from RD to RD, and the terminal function g, which maps RD to R. So this type of architecture design actually approximates function from RD to R by the composition of g and f. Okay, luckily we have the theorem like this. Say that if f has universal approximation property, g strip-sheets and g maps RD to R, then we can prove that G compose curly F, which means that G compose F for all F in curly F has universal approximation property. So this means that we only need to design a class that from RD to RD, which has universal approximation property, and the simple terminal function, which is strip-sheets and maps RD to R. Then we can ensure that G compose curly F has universal approximation property. In general, we can approximate all the Rm value function by choosing a specific G, which will require that G strip-sheets and G maps RD to Rm. Okay, so till now we proved the whole result in one dimension, in higher dimension in one dimension, and the output dimension not equal to input dimension. So it's natural to ask, what does this type of theorem mean? I draw a simple ternary graph here to illustrate my ideas. I want to say that this result actually builds the connection between the approximation theory, neural networks, and control theory. Okay, so let us first see the approximation theory plus neural networks. Yeah, so in neural networks, basically, there are two parameters, the depth and width. Okay, we just take the fully connected neural networks as an example. Here, the depth might be the number of layers, and the width might be the numbers of neurons in each hidden layer. So the natural question is that how depth and width affect the expressive power of neural networks? Or more directly, we want to know that which one is powerful, deep depth or width. So honestly speaking, there are a lot of results concerning about to quantifying the depth and width in the approximation error of neural networks. But here I'm not going to mention these and just to give some qualitative result to help you get a feeling. So we first consider the study of width. The study of width can be condensed into one word is that under given depth, sufficiently wide neural network can approximate any function. This is the very well-known result in neural network approximation. That is that with one hidden layer, sufficiently wide neural networks can approximate any function by a certain choice of the activation functions. And this is already known in last century as the classical result in neural network approximation. And so we consider the parallel problem in the study of depth. That is, under given width, can sufficiently deep neural networks approximate any functions? A crucial observation is that when the width is not sufficiently large, the universal approximation cannot hold. Okay, for example, we consider the one-dimensional result if we consider the input dimension is 1 and all hidden layer to be 1. Say one dimension, one dimension, one dimension, and output is 1 dimension. So definitely there must some information be lost during each nonlinear step. So it can be demonstrated that if the width is equal to the input dimension, then the universal approximation cannot be expected to hold. So there are a lot of results discussing this. But if the width equals than 2, then according to our theory, we can show that at least it can approximate any continuous function, any continuous and increasing functions. So generally, we can say that when the input dimension is d and the width is 2d, so our theory can be applied to show that we can approximate all the functions from Rd to Rd or from Rd to Rm. So in a word, we study the problem, we study this problem in the ResNet setting and provide a positive answer. And the advantage of this type of study is that we do not require a specific form of activation functions. So next, we see the part of approximation theory plus control theory. Yeah, we find that such approximation problem can be also proposed in the control theory. That is, we can consider this type of control systems x dot equals to fx, where f is in some control function family curly f. We can define the a sub ft be the family of flow map with time horizon t. And we recall the approximation of the polynomials. We just discussing one thing, that is how the approximation behaves when we let the polynomial degree tends to infinity. And we make a parallel statement here is that how the function class AFT behave to approximate a function if the t, time horizon t, goes to infinity. There's a few results are focused on this before our result. Say the Paris prove that the flow maps are small in category, which means that field diffeomorphism can be exactly represented by the flow maps. But later, Brenier and Gumbo says that universal approximation holds, even if the exacted representation cannot be expected. They said that they prove that the universal approximation property holds if F contains all the Lipschitz functions. With our result, turns out we show that UAP holds if is alpha invariant and contains at least one nonlinear function. So in this sense, our result can be regarded as a generalization of the famous Renier and Gomber's result. But overall, this type of result can be regarded as the Weierstrass theorem of the control theory. That is that we know that how all the AFT from t to 0 to infinity can approximate all the functions. And the standard Weierstrass theorem just say that all the PKs can approximate the continuous functions. So the next thing is that how about approximation rate? Since we can have a very elegant quantification result in the polynomial case in terms of using some Sobolev regularity. So this turns out to be very challenging when we focus on the control systems. And we consider the very simple case. And to be honest, this might be the only case that have totally figured out. We take the ReLU as the example. We consider the following ReLU systems, which is x dot equals to a ReLU wx plus b. Okay, so we first observe that the flow map is homogeneous, which means that the phi of f at f time horizon ct is equal to phi of cf at time horizon t. That means that we can factor this c to here. Okay, by this scaling, we know that if there is no constraint in the right-hand side, then we can always make the flow runs arbitrarily fast. That means that all the AFT are the same and we cannot distinguish them. So we should do some constraint in the right-hand side. So again, so we cannot just simply make the constraint on A or W, since the ReLU function is homogeneous, which means that ReLU Cx equals to C times ReLU X. So therefore, we should fix the norm of A and W to do some normalization. Okay, here we just fix the entry-wise L infinity norm of A and W as 1 and consider the approximation power. Here we can, under this normalization, we can ensure that all the AFT are different. And it turns out in this setting, the time estimate is one kind of range result, since we just want to let t goes to infinity and to discuss the approximation rate. Okay, here is the result in one dimension. First, we suppose that phi from 0, 1 to r is a piecewise smooth increasing function. And next, we suppose that the total variation of the ln of the phi prime is less than infinity. Denote as t naught. Then we can show that phi can be approximated well in AFT for any t is not less than t naught. So this term might be strange at the first looking, but I shall give you some intuition to justify this. Okay, so we do some simple calculations. We say that the flow map of x dot equals to ReLU x equals to max of x and 0. When x naught, the initial data, x naught is greater than 0, then this term is just x dot equals to x. And it turns out the solution is just x naught times e to t. On the other hand, when x naught is less than 0, this term reduces to x dot equals to 0. And it turns out the result is always x naught. So the flow map of x dot equals to ReLU x is like this. And we first consider prime, which might like e to t when x not greater than 0 and 0 when x not less than 0. Then we take the log to get T0, and finally, we take the total variation to get T. So actually, we can do the simple calculation to show that for such a flow map, x dot equals to ReLU x, the time horizon is just exactly the total variation of the ln phi prime. So this implies that the theorem is optimal, at least for one dimension and ReLU case. So for higher dimension, unfortunately, we cannot have such a good result. And so there are some results based on a refined argument, which I simplified as this. So for simple functions f and epsilon, so there is a function phi in the AFT such that it can make sure the approximation error is not greater than epsilon, with the t estimate is the epsilon over for d minus 1. So this means that we still have a long way to get a very satisfactory result in the approximation general functions. Okay, so let's go to the next topic. So in the previous section, we studied the neural networks approximation for general non-constraint functions. And here beyond expressing the arbitrary function, we can also consider some case that expressive some special functions, for example, the invariant functions. Okay, to using neural networks or using some deep structures to approximate invariant functions, this can be categorized into the field of geometric deep learning, and which they might tackle with a lot of difficult things there. But here, I just make things simple and we just focus on some invariant case. So for example, we just consider the permutation-invariant functions. This is also known as set function in the computer science community, since the set function only regards the input as a set, but regards the sequential information. Okay, for example, the summation function, the maximal function, and the product functions. Okay, a relevant topic is the permutation equivariant function, which means that when we change the input parameter by some permutation, then the output should be changed correspondingly. So this is called the permutation equivariant function. So actually, there are some simple functions to preserve the symmetry, to preserve the permutation invariant function. For example, we can construct a simple permutation invariant function like this. We pick any sigma to be a univariate functions, linear or nonlinear, and consider the f from that is the summation of all sigma xi. So clearly, this is a permutation invariant functions. Also, we can consider we first do summation, then go through the nonlinear sigma. But the natural question is that how do we express more complicated function with symmetry? For example, we want to make a class that is both have the permutation invariance and the sufficiently expressive power, say the universal approximation property. A natural way to resolve this is, for example, we have a very good approximator for general non-constraint function and pick one from this, say f. Then we do some averaging to consider the summation over all f pi x, where pi goes through all the permutation functions. Clearly, this is permutation invariant, and the expressive power of the average of f is just the same like the f. But the drawback is that when we do this type of calculations, we need the factorial of n copies. And this turns out to be very time and memory consuming. So instead of adding instead of the averaging techniques, we should find some other techniques to construct some neural networks to preserve the permutation invariance and the universal approximation property. So we can consider the problem in a very general setting and to see the difficulty we confront. Okay, so now we model the symmetry as some group G. And we say that the function is called the permutation invariant if the phi of gx equal to phi x. And we also define the permutation equivariance when the psi and g commutes. So we want to answer the question is that how to construct a neural network with both symmetry and expressive power. And we found that the balance is inevitable since the symmetry constraint is closed. Okay, here's the theorem. We say that suppose all the function in some function class curly G are invariant with respect to some group H. So if phi can be approximated well by the functions in this G, then we can show that phi itself is H invariant. So this proof is also a straightforward one-line argument. We first, by least lemma, we know that there exists a subsequence that converges to phi almost everywhere. And using this, we can conclude that phi is invariant with respect to H. So this means that if we use the H invariant function to approximate phi, then phi is also H invariant. So similar result holds for equivariant functions. When we use H equivariant functions to approximate phi, then phi itself must be H equivariant. This means that we should design some architecture that exactly resolve the permutation group we want to study. So we first consider the convolution neural network and regard it as a shift equivalent structure. Here we should do some mathematical assumption. Okay, the ambient space is chosen as any tensor space. And here the shift operator is defined just by shift its index. And we define the convolution in the standard way. Okay, so here we should emphasize that the convolution operator is determined by different boundary conditions. For example, when we consider a zero padding condition, which means that when we touch the boundary, we feel the zero in the boundary, out of a boundary. So this is the case for zero padding. So, but if we consider the convolution is a periodic type, which means that we feel the data outside the boundary periodically, then we can show that the convolution commutes with shift. So this means that the convolution operator and the shift operator can change their position. So for example, we can see these fully convolution neural networks as an example. Here for any FCN block, we show that the input-output mapping is shift equivalent since the convolution is shift equivalent and the ReLU is a component-wise operator, so it must be shift invariant. And finally, we get some summation. So from here to here, we can deduce that the input-output mapping is shift equivalent, which means that when we shift the pixels at here, then the result must be shifted correspondingly. So, and we use the FCN block to build the whole fully connected, fully convolution neural networks. And finally, we do some pooling, say the summation or the maximum operators to get a one-dimensional result. So as a consequence, by this construction, we know that the whole fully convolution neural network is shift invariant. So actually, we can write down its mathematical formulation here. So in each step, we say that xn plus 1 equals to summation of some channels, which in each channel, we have the formulation is that the ReLU W convolution with xn plus some bias. And here we quantify the support of the kernel size. And so here we can have the result is that under the fully convolution neural network setting, under the shift equivalence setting, we have the following result. We prove that the CNN has the universal approximation property if each convolution kernel has a support greater than 1 and the channel number is greater than 1. And also we say that the result is optimal since that if either the support of convolution kernel or the channel number does not meet this requirement, then the CNN does not have the universal approximation property. Okay, so this might be the first result quantifying the effect of the kernel size and the channel number. So we can make some simple remarks to show how we get this optimality result. The sharpness result on the kernel support is that we say that if one of the kernel support is 1, then the convolution mapping must have the following form like this. Actually, all the data will commute inside each row, and beyond the columns, they will not interact. So this type of result can be simplified to a toy model like this. That is, the fx plus gy cannot approximate a general birated function, say the product of x and y. So when we prove this, we can actually get a proof like this. The second remark is the sharpness of the channel is motivated by the fact that the ReLU is an almost linear function. So it might be very difficult if we just use one channel here to approximate a radial function, say hx equals to the norm of x. So this is a true remark for the optimality result. So how do we get this sufficiency result? Actually, we also use the residual structure. The universal approximation for the original FCN is proved by the sufficient condition for this type, so we call the residual version of CNN. And we prove that the residual type of CNN, or its continuous time idealization, has the universal approximation property if the channel number is not less than 1 and the kernel support is larger than 1. So using this, we actually can prove the original CNN result. So this is the approximation result for the convolution neural networks when we regard it as a shift equivalent structure. And also we can also design some neural networks for the permutation-invariant case. Okay, here we propose a residual version of the deep sets, which is studied by Zahir and his collaborators. Okay, here, for example, we can consider the controls family as the A of sigma WX plus the average of X and plus some bias. So for a given input, each residual blocks marked like this, we first consider its averaging and do some summation and get the bias. And finally, we go through the nonlinear functions. And also we can consider a more complicated control function family. So we can show that, suppose that under some general conditions here, we can show that for the f equals to this one choice or this choice, or the G compose AF. Here, G is the averaging operator, has the universal approximation functions. Okay, therefore, we can obtain some universal approximation property guarantee for general activation functions, because here we require very simple conditions here for the activation functions. Okay, also we can consider some nonlinearity involved to get a more complicated expressions. For example, we consider a residual version of the generalization pooling. So here we consider the one generalization pooling as V sigma AX plus B, the summation of Vx plus C for all real VABC, and the two generalization pooling to incorporate some pairwise interaction. For example, we choose the F2 generalization pooling as the V sigma AX plus B for VXI XJ plus C. And the result is that we can prove the universal approximation property under some mild conditions. For example, we can show that for one generalization pooling, the UAP holds if phi is 3p's and there is this neighborhood phi 0, such that the inverse of U is bounded. So this holds for very general functions. And second is that for the two generalized pooling, we can show the similar result, that is UAP holds if phi is symmetry and phi x0 satisfy the previous one generalized pooling conditions. So here we use the residual blocks to design some new neural network architectures that satisfies both the permutation invariance and has the universal approximation property. And the highlight is that here we can obtain the UAP guarantee for very general activation functions. Okay, finally, also we can consider some type of result that is beyond the permutation. It will be very a little general. So we generalize the above idea to some more complicated case. That means we consider the product of permutation invariance. For example, we say that here the input is a D1 by D2 matrix, and output is invariant and equivariant if we switch each two columns or each two rows. So for example, we can consider the absolute value of a determinant. So it will be invariant if we just switch two rows or the two columns, since we use the absolute value to guarantee this. So the way to resolve this is we want to construct some basic operators like the averaging operators here. So we consider the reduction operator, which means that we have the row reduction, which means that we get a summation along each row. And similarly, we consider the column reduction, which means that we get the column summation along each column. And also we just generalize the idea of generalized pooling here. We consider the pairwise reduction, which means that we consider pairwise sum along each row and each column. So we can prove that for both setting F1 and F2, here F1 just involves the X itself, the row reduction, the column reduction, and F2 involves about the X itself and row reduction, column reduction, row pairwise reduction, and column pairwise reduction. Then we can show that for each choice of F equals to F1 and F2, the G composed F has the universal approximation property. Okay, here G can be chosen as the averaging functions. Okay, so we do just recap. So we under certain condition, we provide a general constraint for control systems. Again, we show that it's optimal for the residual net. And also we consider the universal approximation property for a control system that's subject to some symmetry, which means that we first consider convolution neural network as a shift equivariance structure. And in this case, we quantify the effect of kernel size and channel number. The second is we consider some construction of the permutation invariant functions, which we generalize the deep set and generalized pooling into a deep case and show it can achieve the universal approximation property. And finally, we study a generalization of the permutation invariant function, say the product permutation invariant, and provide a universal approximation property. So the key advantage of this type of method is that we make no requirements for the architecture specification. That means that we can use a lot of choice of activation functions. And the take-home message is, again, that the composition and stacking layers can achieve expressive power of each layer is quite simple. Okay, so here is the results of our papers. So that's all of my today's talk. Thank you.
Okay, thank you, Ting, for the talk. We have some time for question. Let me just stop the recording.